Okay, welcome back. Let's continue to our course on optical flow estimation. Now, until now we have seen techniques based on uh, solution of the optical flow constraint equation. Now we are moving to some other techniques based on matching. The first technique is something called block matching, which is very popular in video compression. Now, again, we have the same idea. We have to find a representative of a pixel or a region which will match the intensities between consecutive frames. Right now, here in block-based techniques, what we assume is the motion vector within this region will be constant. Okay, therefore, within this block, we will assume that the motion displacement will be constant, and we will try to find the intensity differences in those blocks after moving the block into a region. This time, the thing is, we have a block. We are trying to match the corresponding at the next frame. Okay, therefore, for this block, we will look for a search range in the next frame. Okay, then what we're gonna do is basically we will take this block and we will look for everywhere in terms of the pixel differences at those points in underneath. We will look the some of these differences, okay, and we will just try to check whether that makes a minimum or not. Okay, therefore this concept obviously a little bit computationally costly, because if there are n by n pixels here, if the search space is much bigger with respect to your size of the block, then you are looking to many pixels in this search area one by one, and at every such point I have to make like n squared differences. But nevertheless, it's a relatively a very fundamental technique, which is matching a template and looking for a equivalent or similar of the template in the next frame. It's also very computationally intensive but hardware friendly, because at the end we are simply doing pixel differencing and absolute or square summing. Okay, therefore there should be a search space defined and there should be a block size defined. And finally, the search algorithm. Obviously, one technique could be just looking one by one every pixel, which is called full search. Every block, for a block right here, we will just assume that we will move this block to every pixel one by one, and we will try to estimate our error over there. There could be some other techniques. Okay, this is a three-step search technique. In other words, once you are looking for your candidates, you first look around the those 9 points here, okay, which are relatively not only a single pixel apart, but it's like 3 pixel apart. Therefore, you go over there and you, for the three-step search algorithm, you find the best for this 9 candidates. Now, then you move to here and you just look for your candidates around a smaller neighborhood where centering is this new candidate. Assuming that this is your best result, then you again this time maybe make your neighborhood only a pixel apart from each other, and you will obtain your best result based on this point. This is called the three-step search algorithm. This is the log search. Again, this time you are going in a fixed size neighborhood, okay, and you look for your 4 best results. Based on that, you move to another, and at the end, after a few steps, you will go and you make your final refinement like that. Therefore, this is a very fundamental technique, and you have to implement these things in hardware. All our mobile phones, all our digital televisions, anywhere, or even this YouTube video servers inside, there should be some encoders and decoders working in hardware. The encoders looking for some motion vectors between the frames so that the redundancy within a video is removed. But it's a very fundamental, simple technique. When it is implemented in hardware, it's also very fast and cheap. But unfortunately, we have some problems with the sub-pixel localization. Note that you can only move 1 pixel apart, therefore your results should be interpolated by somehow. The typical idea is you enlarge your images by 2 or 4, then you do the same thing, but your results become half pel accuracy or quarter pel accuracy. This is a typical, the best way to obtain sub-pixel localization. Okay, sometimes these results not give very good because the MSE could be a little bit erroneous due to many reasons, but nevertheless it's a relatively popular technique to check an estimate for displacement of a pixel. For every pixel you have to do this within such a grid. This is a grid which is basically disjoint here, but you can make overlapping grids as well, overlapping blocks as well, and you can even try to find match for every pixel by just moving your block pixel by pixel with the same block size of n. Okay, now let's go to the parametric, because parametric is also important, especially when the camera is moving, when the scene is stationary. Most of the pixel displacements obey a geometric rule. Parametric techniques basically try to exploit such an idea. Therefore, it is believed that all the pixels are moving as a large object or a camera motion of a stationary scene. Therefore, there should be a relation between those objects. Now, typical parametric models are called affine. Okay, and this is, as I've said before, like a 6-parameter thing. In an affine deformation, such an object will move to these kind of different geometric deformations. Okay, therefore this is typical deformations that you can obtain by playing with A0, A5. Okay, a perspective is somewhat more general. Obviously, you can obtain these kind of apart from the affine ones. Obviously, when you say A7 and A8 is equal to 0, these are equivalent to each other. Okay, but if you make these things also variable, for example, a square can be geometrically warped into this using such an idea. Now, would you please look here? Once you look to a real square with a camera, and when you look at the this planar scene from a little bit from left or right, this kind of a perspective deformation can be obtained. And in fact, perspective models are perfect approximations or perfect representations of planar scenes. If your scene is planar, every pixel obeys this kind of a mathematical relation. In other words, in one image, if you are this coordinate x and y, in the other, the x prime, y prime will obey this based on the estimated 8 parameters or 9 parameters. Now, for unknown parameters, we have to solve them, this A0 to A5 or A0 to A8. Now, the way we solve this is basically is achieved using least square solutions over the all pixels within a region. In other words, maybe you will first, in the corners, you will solve for KLT, then from all the KLT points, you will try to find a least square solution by giving those points x prime pairs. You will solve for the parameters for all the pixels. Please note, in such a solution, we are obtaining a dense solution. These parametric forms are correct for every pixel. Therefore, for sparse points, you have some ground truth x, y, x prime, y prime pairs between two images. You can solve for A0, A1, A2, and you can solve for every pixel which is obeying this parametric model. Another technique could be taking writing the optical flow constraint equation here, okay, and which is equal to be 0 ideally. you are just writing every x prime y prime in terms of this parametric form. Therefore, given the points here, x and this differences, okay, you can write this equation. You can write this equation only as a function of a. Therefore, minimization of this thing on the whole image, on the whole region, okay, the summation within the whole image, maybe in the whole region where the parameter is true. Therefore, you have to take the derivative with respect to a and equate the 0 for every parameter, a0, a1, a2, it goes on like this for every parameter. Now, the Canada-Lucas solution, in fact, in their original paper 81, they have solving their solution through such a scenario, not only two u and v vectors that they are doing horizontal, vertical. In fact, they are solving using minimization of such a constraint equation, like a generalization of this displacement that we did before. Okay, now let's talk about the frequency-based approaches a little bit. Okay, now the frequency-based approaches is a completely different idea, and I'm gonna talk on this in the upcoming slides in the new other tracking techniques that I'm gonna talk. But let's try to understand it for only having two consecutive frames. This is called the phase correlation method. The idea is this. If you have two frames where there is a translational motion in between, okay, then the corresponding 2D Fourier transform has some specific properties, okay? Therefore, if you look at here, let's assume F1 and F2 are the two frames at T1 and T2. Assume one of the frames is nothing but exactly equal to the shifted, displaced, translated version of the other one. Therefore, F1, if you just shift by 5 pixels, 7 pixels here, to the left, to the top, and you will obtain nothing but this other frame. Now, if we have such a relation between the time domain signals, from the Fourier properties, we know that the corresponding 2D Fourier transforms should obey this thing. This is the famous time shift, or here nothing but the displacement shift property, where you have an u and v displacements, okay? That u and v displacements are basically giving or coming into the relation here as a exponential phase factor between 2D transforms of these two frames. Therefore, the 2D Fourier transform of the first frame and the 2D Fourier transform of the next frame is related based on this complex exponential multiplication whose phase is storing this u and v information. Okay, wx and wy are our horizontal and vertical frequency parameters, dimensions in 2D. Now the trick here is, if I take one of the Fourier transforms, if I multiply with the conjugate of the second transform, please note here, if you take the conjugate of this guy, which is plus here, and that will be nothing but a conjugate here. Therefore, this conjugate and that one will bring a magnitude square, okay? And if you just divide the magnitude of this to the for every frequency, if you divide the magnitude of the numerator to this one, you will obtain this complex exponentials remaining here. Therefore, at this point, please note, I just simply take two 2D DFTs. I take one of the conjugates. I just multiply them for every frequency one by one. I just divide by their magnitudes. I look at their only the phase information. In the phase, you will have their complex exponentials where the phase information is in terms of u and v here. And if you take an inverse 2D DFT, those complex exponentials becomes nothing but shifts in the time domain. Therefore, what we are saying here is this fact. By taking the Fourier transformations of consecutive frames, assuming there is some translational component between those frames, Just multiplying one DFT with the conjugate of the other DFT and remove the magnitudes. The phase will consist of nothing but the information about the displaced pixel, the displaced optical flow value UMV, and it will give you nothing but an impulse, a peak, a strong peak in the XY domain. And if you do so, we will obtain nothing but our position of the unknown U and V translating components. Therefore, just taking 2D DFTs, multiplying, getting the phase and inverse DFT is giving us an ideal impulse, where that impulse position in the XY domain is nothing but the translating components that we are looking for. Now, obviously, this location is basically obtained by the velocity information, the unknown velocity information, and we can improve this algorithm by trying to obtain a sub-pixel displacement estimation by trying to fit a quadratic to this output. Please note, in the ideal case, there could be a perfect impulse, but typically in real life data, this inverse operation will give you nothing but a Gaussian bell-shaped, maybe a small bell-shaped object waveform. Therefore, we will have to fit a quadratic to this output waveform, and if we find the maxima in a closed form, taking the derivatives of the Gaussians or peak values, you can find a sub-pixel positions. And please also note one more thing. You can apply this idea not to the whole image, but you can divide your image into some local blocks and individually apply this into individual blocks, so that local motion information can also be estimated robustly. You can also make it apply it in a local way, but then just accumulate the resulting phases and take an inverse transform to obtain a robust general solution. It's a well-known technique. It's a very fundamental, ideal technique, and I'm gonna show this shortly after this video in the next tracking part. A family of algorithms are basically depending on this concept and giving very promising results. Now, for the phase correlation, if you look at here, this is our very ideal data. A square is moving into some point arbitrarily here. If you take their DFTs and if you just multiply with their conjugate of one of them, divide by the magnitude, the resulting phase is nothing but like that, which is UWX plus VWY here. That's a planar equation, okay? And the corresponding H of XY will be nothing but an impulse, okay? Obviously, first of all, maybe we have to state something, we have to remember something. Whatever I was talking was true for continuous data. If your data is discrete, you have to deal with DFT, discrete Fourier transform, and for discrete Fourier transform, you have to have not shifts, but circular shifts. Therefore, with circular shifts, you have to have such a beautiful impulses, but in real life, obviously, when I move from here to here, there is nothing coming from the circularly from the other side. Therefore, all the things I have told you until now is based on the assumption of a circular shift. If it is not, therefore, people are using some tricks. What they do is a windowing, multiplying the image with a Gaussian window so that the periphery of the image is a little bit dark, okay? Therefore, let's assume this is the image. You just multiply with a Gaussian where the peak is in the center. The periphery is getting darker. Therefore, once you assume that there is a shift here, those black parts are entering from here back again, and that brings a better peaky behavior if you don't use a windowing, if you just simply apply naively such a shift from one side, some new data coming from the other part, the results will be not very effective. Okay, for non-band limited signals, you have to have some high pass filtering. Uh, if you have some peak spreading, okay, therefore not necessarily an impulse, you have to have as I've said before, a quadratic fit, maybe a local maxima selection. Independent moving objects, if you just divide your images into multiple parts, or even there could be multiple peaks, okay, there could be multiple peaks due to multiple objects, and you can select the peak after this registration, okay. Now for subpixel resolution, as I've said, fitting a surface will do the job, okay. You can find the peak afterwards. And local partitioning, not necessarily the whole image is moving with the same translation. If you divide it into some local patches, the result will be much better. Okay, that's the frequency-based techniques, finding the unknown displacement between frames. I will come to that later on in my tracking part. Now finally, I would like to talk about another technique called layered motion estimation. That's also a very important idea. In practice, until now, I was always talking about optic flow of everything is smooth, the object is moving, or I was talking about parametric things where we are fitting a parametric to the whole pixels. But in real life, maybe the camera is moving, my hands are moving, something in the background is also moving. In fact, there are different layers, and for all these layers, we have to estimate the individual motion. But unfortunately, we don't know the layers as well. Therefore, for a good approach, we have to find not only the displacement of the layers, but we have to also determine the boundaries of the layers as well. Now, just assume this result, okay? We are talking about an intensity map here, okay? There is an alpha map which is showing the boundaries of the object, like a segmentation mask, okay? This is the alpha mask. Now, let's assume this is the background object with alpha map is this, and which is showing their velocities. The background is moving like that. Maybe the camera is moving in this way, therefore the background is moving like that. This is the other object, the second layer. This corresponding boundary of the layers, okay, the hand. It's waving, doing such a motion here. Now these are the frames. We are doing like this, but please note the background is also moving at this point. The background checkerboard is going down. Now I am trying to estimate a very complicated looking motion. Some of the pixels are due to hand, some of the pixels are due to background. But the trick here is this. If you are able to divide into some layers, then for every individual layer we can obtain a model, typically a parametric motion model, and we can try to find the boundaries from the similarities of the motion vectors in a region. Okay, therefore the idea is this. If we can group the pixels as objects doing the same motion, we can estimate the motion much better. There will be no more smoothness problems or problems due to some boundaries. We will not have those kind of problems. Okay, therefore we have to have a parametric motion model here. That's important. Parametric motion. Therefore I'm gonna fit a parametric form to here. I'm gonna fit a parametric form to here. Okay, now the idea will be like this. It will try to estimate an optic flow, and after estimating the optic flow, we will try to segment it, group it into a coherent motion. With the coherency is checked by the parametric forms. Okay, then we will just look which pixels, which motion vectors are obeying to this parametric form, which are not, and based on this we will continue like that. Okay, this is a technique by Wang and Edelson. Okay, in 1994, we are having this kind of an approach. Either affine or perspective parametric models are being used right now. And now what we are doing here is you can just try to estimate the parametric motion at disjoint patches and try to cluster them. Let's go over this example here. That's the famous flower garden video sequence. Okay, we have the nothing but a moving motion of the camera. This is moving very fast due to parallax. This is moving at a different speed. That's also moving at a different speed. The stationary, more or less the background is the sky is stationary. Now, if you look at the flow vectors here, they could be estimated locally in any kind of technique. Okay. The first thing we're gonna do is we will try to fit a perspective model to hold to these all motion vectors together. If you do so, you will obtain nothing but a good fit for the general motion that we obtain. In other words, assuming most of the pixels are on this planar scene, giving a good perspective fit, the parameters of this region will give you your first parametric set. Okay, there will be 8-9 parameters here which are basically fitting to whole pixels here. Therefore, the error between the pixel displacement here and the model here will be very small. In the meantime, the motion vectors on the street, the motion vectors behind or on the houses, they will have high errors. Now the idea is this. Therefore, after the first step, after fitting a parametric form to the majority of the pixels, you will take those pixels and assume they are inliers and remove all the others. All the others are the ones on the trees, the ones on the sky, the ones on the houses. Now, after removing those motion vectors, we will apply the same parametric motion estimation stuff to the remaining part. Okay? Therefore, we will try to fit another parametric model to this tree, to the sky, and to the houses. And note that every part, at every step, we are obtaining a group of pixels whose displacements obeying one parametric model. In fact, the boundaries of those pixels as shown here, these are showing us nothing but the first parametric model, and that parametric model is our first object whose parameters are given A0 to A8, whatever. Then we do the same thing, we obtain the result for the houses. Then we will do the same thing, obtain the result for the tree, and we will obtain parametric form not only for the layers and obtain the boundaries of the layers, but also the parametric equations for every boundary as well. Therefore, layered motion estimation is important. When you have a complicated, a practical scenario, camera is moving, objects are moving, there are different things, at that point we have to have such a layered motion estimation result technique, so that we not only find the boundaries of the moving objects, also the parametric motion vectors. Okay, that's the other technique. Now that concludes our OpticalFlow estimation from 2 consecutive frames. Now in the upcoming video I'm gonna talk about nothing but our estimation within a video sequence for a long period of time. How do we do tracking, visual tracking from the video frames.